Going on now to topic 2 of chapter 9, exponential functions. And these are the sections we'll be going over. In this section, we introduce a new type of function, the exponential function. These functions and their inverses are called logarithmic functions and have applications in many fields. Consider the graph below. The rapidly rising curve approximates the graph of an exponential function. We now consider such functions and some of their applications. And this deals with the development of text messaging in the United States. And as you look from 2003 to 2008, it seems to really be taking off. Now, this is in contrast, sorry about that, to something that might have looked like a straight line. This would be linear. This type of curve is referred to as exponential. And you may have heard that when something is really growing fast, we say it's growing exponentially. But what's the math behind it? So in chapter 7, we studied exponential expressions with rational number exponents. And it was 5 to the 1/4 power, and then these other examples. I don't recall doing those with decimals, but that would be another form of fraction. Now here they're just showing that if you have them in this exponential form, that as you add decimal places to make the number more and more precise, we define then 5 exponent square root of 3 to be the number p, that is to 8 decimal places. And we'll be hearing more of that later. Any positive irrational exponent can be interpreted in a similar way. Negative irrational exponents are then defined using reciprocals. You might recall that from our study of exponents, an example of which would be 4 to the 2nd power, and its reciprocal would be 4 to the -2 power. So here it's just 4 times 4, which is 16, and this, you recall, is 1 over 4 to the 2nd, or 1 over 16, and that is its reciprocal. So a little extra information on that. So we can now define exponential function. The function f of x, which is our function notation, is equal to a to the x power, where x is our exponent and a is a positive constant, but cannot be equal to 1. So we define it as this could just never be 1, because 1 to any power is always just 1. So we exclude 1 from it. Okay, let's go on. says we require the base a to be positive to avoid imaginary numbers that would result from taking even roots of a negative number. And that goes to the last part of chapter 8, or 7, I should say, when we were doing imaginary numbers. A little review of that as we think of our final exam coming up. So we said the square root of any negative or even root number was imaginary. And we took out the -1 to convert it to that form. Okay, the following are examples of exponential functions. And note that this right here, we could think of this as, in parentheses, 5 to the -3 raised to the x power. That's going to be useful when we compute these later. Okay, like polynomial functions, the domain of an exponential function is the set of all real numbers. Now again, we're talking about the exponents because we're saying the base earlier cannot be equal to 1. So we're talking domain of the exponent up there, not the base, as all real numbers. Now, because of this, graphs of exponential functions either rise or fall dramatically. And that's what gives rise to that word exponentially. Something grows exponentially. The rise or fall is dramatic. All right, let's look at our first example. And again, as we go over this, what we're doing is reading the textbook, studying it, thinking about it, trying to relate it to things we perhaps already know, and have it become part of our math intelligence, so to speak. So here we're going to graph the exponential function where x is our exponent and 2 is our base. So we could put it in a little t-chart, but remember, these are our exponents. So 2 to the 0 power is 1. So remember, that's where our x goes, right up there. 1 as an exponent. 2 to the first is 2. So that'll be 2 to the first power. Now, 2 to the second power is 4. 3 to the, as an exponent, 2 to the third power is 8. There we go. All right, now if we switch to negative exponents, 2 to the -1, believe it or not, that just goes down, and that is 1/2. 2 to the -2, that would be 1 over 2 to the second is 1/4. And 2 to the -3, this would become a 3 down here, that's 1/8. And can you see their reciprocals? Now, if we go to graph this, fortunately, they have it all worked out for us here. So we don't have to do it. There's our little t-chart. And as we plot the points in, this gives us our basic shape of our curve. Now, as it goes down, this line becomes very, very close to the x-axis, but never quite touches the x-axis over here. And this is a typical plot of our curve for exponential function. Now, if I were a student, and I am in a sense a little bit always, I would take some notes on this and see how we get it. Note that as x increases, our values of x increase, the function values increases without bound. It just goes up there. As it decreases, that is, we get negative exponents, it gets very close to 0 on the x, but never quite reaches it. And again, you'd have to have a very large magnifying glass toward the end. Okay. So now let's take a look at example 2, where we are now going to raise a base that is 1/2 two exponents. And let's take a look at this. Now we have our same t-chart. Again, these are our exponents, and our base is 1/2 raised to our exponent. So if our first value of x is 0, we said anything to the 0 power was 1. If our exponent is 1, then this just becomes 1/2. If our exponent is 2, then this becomes 1/4. If it's 3, this becomes 1/8. Now, notice if we start going into exponents that are negative, and let's just show you that one. That would be 1/2 to the -1. We had said a technique earlier was if you have a fraction to a negative exponent, all you had to do is flip it, that is, take its reciprocal, and the exponent then becomes positive. So, in a sense, when you have negative exponents here, you're going to take the reciprocal of that and it becomes a whole number. So 1/2 to the -1 power is actually 2. -2 power is 4. -3 power is 8. It's the reciprocals of these. So if you're catching on to what's going on here, that's going to be very useful. So now let's take a look at the graph. And what we've done here in this graph, this was our original one where these were whole numbers and the dotted line is this curve. Now notice what happens when these are fractions, like 1/2, the reciprocal of that, and then we apply our exponents in this chart, what happens? Can you see you are getting a reflection of what it was over here with your axis of symmetry being the y-axis, and both of them going through 1. Wow. And that's what they're saying here. Next, we plot these points and connect them with a smooth curve. This curve is a mirror image or reflection of this curve that we did in example 1 across the y-axis. Okay? Now, one thing we didn't mention, and I should have, is that we have a horizontal asymptote here, which is y equals 0. And what is y equals 0? Well, that happens to be the x-axis. So the horizontal asymptote, and again, these lines never quite reach it, y equals 0 is the x-axis. So again, you're going to do some practice, but try, and again, take this, include it in your notes so that this serves as a reference. It doesn't have to be a super exact diagram, but something like this. Now, in our textbook, they do give us this interactive discovery, which is what we've talked about. Now, if we have, let's say, 2x, and this value is increasing, that is, becoming larger numbers, our curve goes up. It's an increasing function. If we have things like 1/2 to x, and as this goes up, our curve is actually decreasing. It's a decreasing function, as we see here. Okay. And here are some things to think about in reflection as to what is happening. Well, this would be increasing. This one would be increasing. This is going to be increasing. But this one, because it's a fraction, would be decreasing. And this fraction also decreasing. So how can you tell? Well, if a is a whole number greater than 1, it's going to increase. If it's less than 1, it's going to decrease. All right, compare these graphs, and we'll skip that for now. Okay, because we don't want this to get to be too long. Okay, now we're going to take a look at these lines. Now the one in black is a 2 as a base. The one in red is a 3 as a base. Which one is increasing more? The larger base is increasing more. And that will be a trend. 4 will be in there, 5 will be in there, 6 will be closer to the y-axis. Now, let's take a look at this. Here we have 1/2. That's the black line. That's a larger fraction than 1/3. Well, where do you think 1/4 would be? Again, closer to the y-axis on this side. So if you had 3/4, that would be out here more. Okay? So the smaller the fraction, the closer. The larger the number, the closer. So it gives you a little bit of summary or a little bit of idea of what's going on in regard to these numbers, so that when you are asked to say which graph is which, you ought to be able to pick it out. And again, I would make a sketch of this for my class notes. Let's go on. So here they want you to graph this function, and it's going to be a value of x, and whatever that is, minus 2. So as you put this in your table over here, let's analyze it. So if x is 0, let me put it up here, 2x minus 2. So if x is 0, this is going to be 2 to the negative 2, which is 1/4. If x is 1, this is going to be 2 to the negative 1, which is 1/2. 2, if this is 2, 2 minus 2 is 0, and 2 to the 0 power is 1. And then if this is 3, then this becomes 2 and 4. And if you have some negative values in there, a negative 1 and a negative 2 is negative 3, which is 2 to the negative 3 is actually 1 over 2 to the third, which is 1/8, and so forth. So these are your points. Now let's look at the graph. Now here, this is also critical. So if you look at this first graph where we have 2 to the x power, which is the dotted line, and you have 2 to the x minus 2, which is this red line here, what do you notice about the graphs? And if we go to this point right here, what's happening? We are shifting, or the official word is that we haven't used because we skipped that section in chapter 8. It's called, we have translated, shifted, moved that graph over to the right how many units? Just look right here. And the answer is 2 units. And you might say, well, what's the connection? What's the shortcut we can do to kind of know this right off the bat? Well, you will find that if in the exponent it says x minus 2, here's the key. We're going to shift that 2 units to the right. In a sense, the opposite sign. Now we have mentioned that before, that when you see something in there, we're shifting it in the opposite direction as to the sign. So here it says -2. We're actually shifting it 2 units to the right as if it were a +2. So that's the shortcut. And again, this sketch would be invaluable in your class notes as to what to do when you see something like that. All right, let's continue. Again, y equals 0, or our x-axis, is the asymptote. Now, they're giving us a little formula here that it's 2x to the -h. If it's a -2, that is, we're going to shift it to the right, opposite sign of this. Okay? Now they give you a little chart of summary here that may be useful. So if we have that, the graph is translated to the absolute value of h, which will be positive. So units to the right, if it's positive itself, it's going to be units to the left. And that's about what we're going to say here. Our constant would then shift it up or down a little bit, and that'll be closer. If this number base gets larger, remember our previous diagram, and I'm not going to try to describe it without looking at the diagram. Okay, now we're going to look at our next little part in which equations with x and y are interchanged. All right, let's take a look at this. So what we're going to do here, that so far we've been dealing with this, y equals 2 to the x, where x is our exponent. We're now going to reverse the x and the y, and we're still dealing with our 2, our sort of an old friend, easy to work with. And now we're going to start filling in our chart, because now our y value is 0. What will our x value be? Well, a 1. Our y value is 1. What will our x value be? 2. And if you continue through this, you get these. So these are now the x as a result of y as our exponent. We have interchanged this. Now let's take a look at what our graph looks like. Okay. So again, we have a curve, again, a typical exponential curve. But now here, this one reflects, and if we put it together here with our old one, can you see that this is sort of, well, not sort of, is the inverse of this? And our axis of symmetry is y equals x that we had in section 9.1. And our asymptote, by the way, for this blue line. Instead of where this one it was the x-axis, now for the blue line is the y-axis. Now, what do you need to do to master this? Well, again, it's looking at your diagrams, your charts, your calculation, and studying it. So and again, I'd make a picture of this one. This is in a sense, the reverse of what we've been doing. All right, going on to the last section here, we are going to look at applications of exponential functions. Interest compounded annually. Here the amount of money A with this principal will be worth after T years. Now we had some problems like this where we're trying to find the interest or the rate there before. And here we're going to try to solve for T. So if we put T in there, we find that through the process of putting various numbers in there, look what happens to our curve. And you might say, well, what kind of curve is that? Exponential. Now, where does this fit into anything? Well, it just goes to show you that if you, as you start to think about retirement, can start something small on a weekly, and it's going to be compounded annually. Now, the thing about this is that this was at 8%. Well, nobody gets 8% anymore. Some of the stock market has done this, but it used to be if you got 6% interest in savings, but lately it hasn't been like that. But here they're just trying to show you that when you have a pretty good interest rate and it's compounded annually and it results in an exponential buildup, that your money can really grow into something. Wow, in 10 years, 100,000 grew into that. But that's at 8%. You don't get 8%. Now the rates are like 1.2%, and that would be doing well. Okay, well, you're going to do your practice. I would suggest you do the practice first so that when you take the quiz me, you know what to expect and can get the help as you do it. And good luck.